Okay, in this video we're going to look at two examples. In number 2, we're going to find the angle and the point of intersection between this straight line, which we call L, and this plane. Then in number 3, we've got two planes. We want to find the angle of intersection between these two planes. We want to find the line of intersection between them. So let's get on with number 2. So just a bit of background. So when you have a plane, so again in the sketch we're just going to assume that the plane is horizontal, so that is our plane. And then if there is a straight line that is not parallel to the plane, then the straight line is going to intersect with the plane. So this could be our straight line, for instance. That's going to be the point of intersection. The angle of intersection will be taken to be the smaller angle between the two. So if this is the normal of the plane, so this is 90 degrees, so the angle we're interested in, well, is this one here, but we are going to calculate this one, and then if we know this one, we can get this one by subtracting from 90. But the first thing I want to do is to find the point of intersection. Of course, if the line is parallel to the plane, if we try to solve that situation, it's going to show us that it's impossible. But yeah, because they say find the point of intersection, then we imagine that that is going to be possible. So the thing to do if we're finding the point of intersection, so you can see we have got three variables here and 3 variables here. So we try to do it using the x, y, z variables. It's really going to be a bit complicated. So what we are going to do, because we know the equation of the straight line, we can express it in parametric form, in which case we are just going to have one variable. So if we equate it to the parameter t, then x is 2t plus 5, y is going to be 6t minus 3, and z is going to be 4 minus 3t. So that is the form we're going to use, where we only have got one unknown or one variable t. Then we're going to plug that in to this scalar form of the equation of the plane, and then we're just going to have one variable, an equation for one unknown. So x is 2t plus 5, y is 6t minus 3, z is 4 minus 3t. This is equals to negative 15. So we're going to have 2t minus 12t minus 9t. And then on the other side we're going to have negative 15 minus 12 minus 6 minus 5. So let's see, 2 minus 12 is minus 10, so this is going to be minus 19t. minus 15 minus 12 minus 6 minus 5. So let's see, minus 15 minus 15 minus 12 minus 6. Make sure I'm still remembering this. Minus 5. This is minus 38. So t is equals to 2 at the point of intersection. So if we go back to our parametric equations here, and we just plug in t equals to 2, then we've got the point of intersection. So that's going to be 4 plus 5, that's x, and y is going to be 12 minus 3, z is going to be 4 minus 6, which works out to minus 2. So that is going to be the point of intersection. Now we need to find the angle of intersection, this one here. So what we are going to do, we need the direction vector of the straight line, which we can find from the parametric form. Direction vector of the straight line, I'm going to find from the parametric form of the straight line. It's just going to be the coefficients of the parameter. So it's going to be 2, 6 minus 3. 2, 6 minus 3. We need the normal of the plane. It's just going to be the coefficients of the x, y, and z variables in scalar form. It's going to be 1 minus 3, so 1 minus 2, 3. 1 minus 2, 3. So then the angle between the two of them, if we call it phi, it's going to be this one here. The one we're looking for is theta. Phi plus theta is 90. Okay, so theta will be 90 degrees minus phi. Phi, we already did this in the video on the dot product. So it's just going to be the inverse of cosine of m dot n divided by the magnitude of the two, what the product of the magnitude of the two. Do the dot product quickly. It's going to be 2 minus 12 minus 9. 12 and 9 is 19. 2. Do this in the calculator. So it's 2 minus 12 minus 9. 2 minus 12 minus 9. It sounds like 19. Negative 19. Okay, 2 minus 12 minus 9 is giving us the dot product is negative. Okay, but you can see that phi must be an acute angle, because so when the dot product is negative, it means the angle between the two vectors is going to be bigger than 90, between 90 and 180. But you can see that phi must be acute because phi plus theta must add up to 90. So what it is telling us, it's just a matter of orientation. It is telling us that if n is like this, and our direction vector is like that, and yet we want, so it's giving us this angle here, we want this one. So instead of taking, so there are two things we can do. Either we take the negative of m and go that way, then we're going to have an acute angle, or we take the negative of n and go that way, and we're going to have an acute angle. So instead of negative, because if you have n dot m equals to negative 19, then negative n dot m is positive 19, because we want an acute angle. So I'm going to plug in positive 19 there. Okay, so theta is 90 minus inverse cosine 19. Then we do the magnitude of each one of them. This one is going to be 9, 10. It's going to be 14. So that's square root 14 there. This one is going to be 36, 40, 49. So that's 7. So if we plug this in the calculator, it's going to give us 46.5. So the angle between a line and a plane is always going to be that smaller angle, the acute one. Okay, so that's number 1. So find the point of intersection, we'll find the angle. Number 2, we've got two planes. One, the angle of intersection, and we want the line of intersection. So let's just bring these down this side. So we are going to start with the angle. We are going to start with the angle. So when you got two planes, the angle of intersection is going to be the angle between the two normals. Okay, so straight forward. So from this one, the normal, which we're going to call n1, are going to be 2 minus 1, 1. And from this one, the normal is going to be as y there. It's going to be 1, 1, 1. Okay, so then the angle between the two of them, theta is going to be inverse cosine. I've already done this calculation countless number of times, even including just in the previous example. It's going to be 61.9. And then for the line of intersection, so we have got again two equations, 3 unknowns. Okay, so that sounds like we are going to have a problem, because it sounds like our system is overdetermined. Yeah, so actually the correct term technically is underdetermined. But that's not a problem, because it means we're going to have a free variable, and that's the variable which is going to give us the parameter. So all we need to do here is to eliminate one of the variables, and then once we have done that, then we work it out. Let me just get on with it. So this is the line of intersection. All right. So if I add these two, simply add pi 1 plus pi 2, then y is going to be eliminated here. So we're going to have 3x plus 2z equals to 7. 3x plus 2z equals to 7. Then we are going to make one of these the subject of the formula. It doesn't matter which one. I'm going to make z. So z is going to be 7 over 2 minus 3 halves x. Okay. Now, the variable on the right hand side here, I am going to make to be our parameter. So if we let x be a parameter t, then z is 7 over 2 minus 3 halves t. And then this actually becomes one of our parametric equations. X is equals to t. Then we need the parametric equation for y. So for that one, we go back to these original equations, n of them, and make y the subject of the formula. I am going to take the one for pi 2. So that one is saying y is 6 minus x minus y. Okay. But we've just said x is t, so this is 6 minus t. Y is here. So minus 7 over 2 minus 3 halves t. So this is all in terms of t now. Okay. So it's going to be 6 minus 7 halves minus t plus 3 halves t. 6 minus 7 halves is going to be, so 12 minus 7 is 5 on 2. This one is going to be minus t over 2. Oh, is it? It's going to be plus t over 2. So it's 1/2 minus 1. So we now have all three parametric equations. Let me just write them down in order. X is equals to t, y is equals to 5 halves plus t on 2, z is equals to 7 over 2 minus 3 over 2t from there. So that is the parametric form of our line of intersection. We can write this in vector form. So x, y, z is going to be 0, 5 halves, 7 halves. So it's going to be a point on that straight line, plus t into 1/1/2 minus 3 over 2. Okay, so that is the vector form of that equation. Still, from the parametric form, we can derive the symmetric form of the equation of the line of intersection if we make t the subject of the formula. So from the first equation, t is equal to x. From the second equation, t is going to be 2y minus 5. From the third equation, t is going to be 7 minus 2z all divided by 3. And so that's going to be the symmetric form of the equation. X is 2y minus 5 equals to 7 minus 2z over 3. This is the symmetric form. This is the vector form. and this is the parametric form of the equation of the line of intersection. Right, brings us to the end of this round of examples.